Episode 80, titled Verification and Validation, Proving the Design Meets Requirements, the focus is on proof as the discipline that prevents surprises after deployment. Many projects fail not because the architecture was wrong in concept, but because no one proved that the build matched the design and that the outcome matched what stakeholders actually needed. The exam tests verification and validation because they represent the difference between "we think it works" and "we can demonstrate it works," and that difference matters in security, availability, and compliance scenarios. Verification and validation also turn requirements into measurable checks, which makes projects easier to close and easier to audit. Proof is not a single test run. It is a set of targeted tests that align with acceptance criteria and that cover both normal behavior and failure behavior. When you can define what to verify and what to validate, you can create test cases that demonstrate success and reveal gaps early enough to correct them. This episode builds the mindset and structure for turning requirements into evidence. The goal is to make proof part of the design process, not an afterthought applied when it is too late to change course. Before we continue, a quick note. This audio course is a companion to the CloudNetX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. Verification checks whether the design matches specifications and diagrams, meaning you confirm that what was built conforms to the documented plan. This is the "Did we build what we said we would build?" question, and it includes confirming that network segments exist as designed, that routing and firewall placements match the architecture diagrams, and that configuration templates were applied correctly. Verification is largely objective because it compares the deployed state to specifications, such as confirming VLAN presence, confirming trunk allowed lists, confirming route tables, and confirming gateway placements. The exam expects you to recognize that verification is about correctness relative to the plan, not about whether the plan meets business needs. A system can be perfectly verified and still be wrong if the requirements were misunderstood, which is why verification alone is not sufficient. Verification also includes confirming documentation accuracy, such as ensuring diagrams reflect the deployed environment, because stale documentation undermines operations. It often includes inventory checks, such as confirming that the correct models, interfaces, and redundancy configurations exist where specified. When verification is done well, it reduces the risk that hidden mismatches will cause failures later under load or during incidents. Verification is essentially quality control against the specification. Validation checks whether the solution meets stakeholder needs in practice, meaning you test whether the deployed system delivers the outcomes the business, security, and operations teams expect. This is the "did we solve the right problem" question, and it often involves user experience, reliability, and security posture as experienced under real conditions. Validation may include confirming that users can access required applications without unacceptable latency, that failover occurs within the required recovery time objective, and that audit logging captures the required evidence. Validation is more contextual than verification because it tests the system in real or realistic scenarios rather than checking configuration lines. The exam expects you to recognize that validation involves stakeholder acceptance and operational usability, not just technical correctness. For example, a security control may be implemented correctly, but if it prevents administrators from performing required tasks in the allowed maintenance window, it may fail validation. Validation also includes confirming that monitoring and alerting provide actionable visibility, because a system that is up but unobservable often fails operational acceptance. When you validate outcomes, you are testing the system against the requirements and success criteria, not just against the design documents. Validation is therefore the bridge from architecture to lived reality. Creating test cases from requirements and acceptance criteria is the key directive because it ensures that proof is aligned to what matters, not to what is convenient to test. A requirement should lead to one or more test cases that define the setup, the action, and the expected result in a measurable way. Acceptance criteria provide the thresholds, such as specific failover times, specific access control outcomes, or specific logging artifacts that must be present. The exam tests this because it expects you to be able to translate a statement like must support high availability into concrete checks like traffic continues during a single link failure and recovers within a specified time. Creating test cases early also reveals gaps in requirements because vague requirements cannot be tested, which forces clarification before deployment. This approach also supports traceability because each test case can be mapped back to a requirement entry, allowing you to demonstrate coverage and completeness. Test cases also help align teams because they define what success looks like for both engineering and stakeholders. When you base tests on requirements, you avoid the trap of testing only what you can measure easily. Proof becomes meaningful because it is tied to stakeholder expectations. Performance validation includes latency, throughput, and failover timing because these metrics often define user experience and service continuity. Latency matters for interactive applications, voice, and administrative control paths where delays are felt immediately. Throughput matters for bulk transfers, backups, and user productivity when large files or media are involved. Failover timing matters because high availability designs are only valuable if recovery meets the stated recovery time objective and if the system remains usable during transitions. Performance validation should be performed under realistic load because many failures appear only at scale, such as when a link saturates or when a gateway becomes a bottleneck. The exam expects you to recognize that performance validation is more than a speed test. It is a structured evaluation of whether the system meets agreed thresholds under expected conditions. It also expects you to consider that failover can temporarily reduce capacity, and that validation should confirm that the surviving path can handle the load without unacceptable degradation. Timing measurements should be taken and recorded because subjective impressions are not proof. When you validate performance, you demonstrate that the architecture delivers its promised service levels. Security validation includes access rules, logging, and segmentation enforcement because security requirements are often central to acceptance and compliance. Access rules must be tested to confirm that permitted flows work and that forbidden flows are blocked, which verifies least privilege rather than assuming it. Logging must be tested to confirm that required events are captured, such as administrative logins, policy decisions, and traffic flows across trust boundaries, and that logs are stored and retained as required. Segmentation enforcement must be tested to confirm that networks that should be isolated are truly isolated, and that routing and firewall configurations do not allow unexpected lateral movement. The exam expects you to view security validation as functional testing of controls, not as a paperwork exercise. It also expects you to validate that encryption and identity requirements are met, such as confirming multi-factor authentication is enforced and that certificate behavior is correct. Security validation should also include negative testing, where you attempt actions that should fail, because only positive testing can miss critical gaps. Evidence from security validation often becomes audit evidence, so it should be documented and preserved. When you validate security, you turn policy intent into demonstrable enforcement. A practical scenario is validating redundancy by simulating a link failure, because this is a straightforward way to prove that failover mechanisms work in real time. In this scenario, you establish a normal traffic flow through the designed primary path, then intentionally disable a link or remove a member from a redundant bundle to simulate failure. You observe whether traffic continues, whether sessions survive, and how long it takes for the system to converge on the alternate path. You also observe whether monitoring and alerts detect the failure, and whether runbook procedures provide clear guidance on what responders should do. The exam often tests this because it is an example of validation that goes beyond configuration checks and proves behavior under failure. It also exposes common weaknesses such as asymmetric routing, missing capacity on the backup path, or misconfigured failover timers. The results provide objective evidence of recovery time and service continuity, which can be compared to the recovery time objective. When you simulate failure intentionally, you remove guesswork and reveal whether redundancy is real. Testing only the happy path is a common pitfall because real outages often happen in edge cases, such as partial failures, degraded links, or unexpected traffic patterns. Happy path testing confirms that the system works when everything is healthy and traffic follows expected routes, but it does not prove resilience or security under stress. Edge cases include return path asymmetry, failover paths that bypass inspection, authentication timeouts during roaming, and rate limit behaviors during traffic spikes. The exam expects you to recognize that validation must include failure and degradation scenarios because those are the conditions that reveal whether the design truly meets availability and security promises. Edge case testing also includes negative security tests, where you attempt unauthorized access and confirm it is blocked and logged. Another common edge case is maintenance behavior, such as rolling updates, where the system must remain available while parts are being changed. If you only test the happy path, you may declare success and then discover critical failures during the first real incident or planned change window. Comprehensive validation, therefore, includes representative failure modes, not just basic functionality. When you plan for edge cases, you reduce surprise and increase confidence. Lacking a rollback plan is another pitfall because validation can reveal problems, and without rollback, you may be forced to accept risk or to endure prolonged downtime while fixes are developed. Rollback planning means defining how to return to the previous known good state if a validation test fails, including configuration backups, version control, and clear cutover reversal procedures. It also means deciding what conditions trigger rollback, such as failing a recovery time objective test, seeing unacceptable error rates, or failing a security control validation. The exam tests this because it reflects operational maturity and risk management, especially in high-impact changes where a failed deployment can disrupt business. Rollback is not an admission of failure. It is an expected safety mechanism, and it must be rehearsed because untested rollback can be as risky as untested failover. Rollback also influences how you deploy because staged rollouts and canary approaches make rollback easier and reduce blast radius. When rollback exists, validation becomes safer because you can test boldly without risking irreversible disruption. A design that cannot be rolled back is a design that must be perfect on the first try, which is rarely realistic. Quick wins include automating checks where possible and documenting results, because automation reduces human error and documentation turns tests into evidence. Automation can validate configuration baselines, confirm route and policy states, and run repeatable connectivity and performance probes on schedule. Repeatability matters because it allows you to validate after each change and to detect drift over time, not just at deployment. Documentation of results matters because stakeholders and auditors often need proof, and responders need reference data, such as failover times observed during testing. Documenting results also supports learning because you can compare future tests to baseline behavior and see whether changes improved or degraded performance. The exam often rewards answers that include documentation and automation because they demonstrate that verification and validation are processes, not one-time events. Automated checks can be integrated into change control so that deployments are gated by passing tests, reducing the chance of pushing broken changes into production. Documentation should be stored where it can be retrieved during audits and incidents, not buried in personal notes. When you automate and document, proof becomes durable and scalable. Including runbook steps in validation exercises is an important operational note because the system is not fully validated unless humans can operate it correctly under real conditions. Runbooks describe how to respond to alerts, how to perform failover, how to recover services, and how to roll back changes, and validation should confirm that these steps are accurate and executable. During validation, you can test whether alerts route correctly, whether responders can access required consoles, and whether procedures are clear enough to follow under time pressure. The exam expects you to think of validation as both technical and operational because many failures occur when responders are unsure what to do or when documentation is outdated. Including runbooks in exercises also reveals whether access controls are too restrictive for incident response or whether monitoring lacks the context needed to act. It also helps train teams, turning validation into a readiness exercise rather than a purely technical check. When you incorporate runbooks, you validate the operating model, not just the infrastructure. This is critical because the best architecture still fails if it cannot be operated. A useful memory anchor is verify build, validate outcome, document evidence, because it captures the structure of proof in 3 steps. Verify build means confirm the deployed system matches the specifications and diagrams, ensuring the architecture is implemented as intended. Validate outcome means test whether the system meets stakeholder needs under realistic conditions, including performance, security, and failure behavior. Document evidence means record the results in a form that supports acceptance, audit, and future troubleshooting, turning tests into lasting proof. This anchor helps you answer exam questions that ask what to do after building a system, because the correct answer often involves both verification and validation rather than only one. It also reinforces that proof must be evidenced, not assumed. When you apply the anchor, you naturally create a plan that includes checks, scenario tests, and documentation. That is the maturity signal the exam is looking for. To practice drafting validation checks from a requirement, imagine a requirement that states remote access must support multi-factor authentication and must log administrative actions. One validation check would confirm that a user cannot access the internal application without completing multi-factor authentication, and that failed attempts are blocked and logged with user identity and timestamp. Another validation check would confirm that an administrator session through the approved access path produces logs that capture connection start and stop, target system, and key actions, and that those logs are delivered to the central logging platform within an expected time window. The exam expects you to tie checks directly to requirement language and to include both positive and negative cases, because controls must both allow the right access and deny the wrong access. If the requirement is performance-based, a validation check might measure latency or failover time under load and compare it to thresholds. If the requirement is segmentation-based, a validation check might attempt to reach an internal subnet from a guest network and confirm it is blocked and logged. The important pattern is that each requirement should produce testable outcomes and evidence artifacts. When you can draft 2 checks quickly, you demonstrate you understand how requirements become proof. To close episode 80, titled Verification and Validation, Proving the Design Meets Requirements, the main idea is that proof prevents post-deployment surprises by confirming both that the build matches the design and that the outcome meets stakeholder needs. Verification confirms conformity to specifications and diagrams, while validation confirms real-world success against requirements and acceptance criteria. Test cases should be derived directly from requirements, covering performance metrics like latency, throughput, and failover timing, and security controls like access rules, logging, and segmentation enforcement. Simulating failures, such as intentionally disabling a link, is a practical way to validate redundancy and recovery behavior under realistic conditions. The common mistakes are testing only the happy path and failing to plan rollback, both of which leave hidden risks unresolved. Quick wins like automation and documented results turn validation into repeatable evidence and reduce human error, while including runbook steps validates that the system can be operated under pressure. The memory anchor to verify the build, validate the outcome, and document the evidence provides a simple structure for planning proof. Your rehearsal assignment is a test case creation drill where you take one requirement statement and produce a short verification check and a short validation scenario with expected results and evidence, because that drill is how you demonstrate proof mindset the way the exam expects. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.